see this floating emoji?
No, not at all, because I see only my slide and the presenter note.
Okay. So you can't see chat either, huh?
No.
Okay.
Last resort, Joshua, feel free to, in my presentation, just tell me that I'm out of time.
Yeah, I think we have to just play some sort of a noise or just like give a verbal warning.
I'll
That's
definitely
good.
tell you when you're out of time, but I don't know if there's a good mechanism for me to tell you that you're 4 minutes in. I don't want to interrupt you 4 minutes in necessarily, and unless you want me to, then I could do that.
Yeah, that's okay for me.
Just give you a 4-minute warning?
Yeah.
Verbally? Okay, I'll do that.
Yeah.
Okay. All right. So officially this has started. It's already recording. Thank you everyone for joining for this virtual session of ICSI 2022 on mining software repositories. We have 6 presentations, 5 minutes each, that we will have the presenters give one after the other. No Q&A at that point, but we'll have a discussion at the end where people with questions can direct them to any of the presenters, and I will moderate. We're going to start with pick who will be, you can share your screen now, pick when you're ready. And so to make sure there's enough time for Q&A, I'm not going to introduce the authors, but feel free to introduce yourselves if you like. And then I'm also going to give 4-minute warnings for the 5-minute presentations verbally. There doesn't seem to be a better mechanism to do that, unfortunately, as the presenters share their screen. So with that said, thank you, Pick. Feel free to start when you're ready.
Okay, all right. And hello, everyone. My name is Pik Pathanamontong Tanunam. I'm a lecturer at the University of Melbourne, Australia. And today I'm presenting our paper titled Auto-Transform, Automated Code Transformation to Support Modern Code Review Process. And this paper is a collaboration with Clark and his PhD student from Monash University. And first of all, what is code review process? Code review is an activity that developers manually examine newly written code in order to improve its overall quality. But despite the benefit of the code reviews, developers reported that for them to switch the content and keep track of the other tasks and reviews. Code authors also perceive that receiving timely feedback is one of the top challenges. Thus, automated approach would be beneficial by automatically applying the common revisions and allow the developer to focus on the complex and critical parts of the software system. And with this goal, there is a recent work has leveraged an approach to automatically transform code from the version before a review to the version after the review. And in particular, they leverage code abstraction and a recurrent neural network architecture to achieve this task. However, the underlying limitation of using code abstraction is that the approach cannot correctly transform code if a new identifier or literal is introduced in the after version. Another limitation of the recent work could be the use of the RNN architecture. And this is because a recent study has raised the concern that the RNN architecture has difficulties in remembering long-term dependencies between the tokens. Thus, the performance of the RNN architecture could be suboptimal when sequences become longer. Therefore, in this work, we propose a new framework called Auto-Transform, which leverages byte pair encoding or BPE and a state-of-the-art neural machine translation architecture called Transformer. And with the BPE, code tokens will be tokenized into subword instead of code abstraction. Thus, the identifier can be reconstructed from subword, although it is newly introduced in the after version. The use of transformer architectures also helps us mitigate the limitation of the long-term dependencies by computing the relationship for each token for all tokens in the sequence. And then the model will better capture the contextual relationship between all tokens in the long sequence. And to evaluate our approach, we compare the number of perfect predictions with the prior work, and here is the results. So first, we find that our auto-transform can correctly transform the method that have new token introduced in the after version, but the prior work cannot. Second, for the long sequence, our auto-transform also perform better than the prior work, even though we consider only the method without new tokens. And the result for the other two study projects also similar. So these results suggest that, our framework substantially improves the prior work for the automated code transformation. And since we use two new techniques to perform this task, we also interested to quantify the contribution of each technique. Therefore, we conduct the additional experiments by using only one of the proposed techniques. And here is the result. And if you look at the first two columns, which are our auto-transform and the one that doesn't use BPE, and you can see that the number of perfect prediction is largely different, suggesting that BPE substantially contribute to the improvement of our approach. And regarding the difference of the model architecture, we also see that transformer contribute to the improvement, especially for the long sequence one. And these observations also similar and suggest that both techniques using our framework substantially contribute to the performance of our models. And we can conclude that our approach substantially improves the prior work, and the result and insight from our work can also contribute toward automated code transformation for the code review process. And this is just a very brief summary of our work. And if you are interested, please check our preprint, which is available online, or feel free to ask the questions. Thank you.
Okay, thank you, Pick. So the next presenter is Max. Max, you can start when you're ready.
Hello, everyone. So my name is Max. I'm an assistant professor at Polytechnique Montreal. And today I'm going to be talking about assisting API example-based misuse detection by using complementary artificial examples. So first of all, APIs suffer from some pitfalls, but here we're particularly interested in one, and that is that by design, users are decoupled from API development, and that's on purpose, right? So API developers create functionality with potentially difficult and abstract concepts that they don't necessarily want to share with their users. And so they build an interface on top, which is the API, and they give those to API users. And then the API users don't have to worry about the underlying functionality, and they can simply use the API. However, the downside of this is that because we don't necessarily know the underlying functionality, we may misuse the API because we don't really understand what's happening. So to counter this problem, misuse detection approaches exist. So there are many of them. Some of them are static misuse detection approaches, which we look at in this paper, and some of them use specifications, which are also good approaches. But one thing they all have in common is that they're quite fault prone. So their precision usually averages between 30 and 40%. And this high false positive rate makes it really tough for the users of these approaches to distinguish whether the approaches are giving a misuse or actually just giving a false detection. So we're interested in looking at how these approaches make mistakes and whether we can improve upon those mistakes. So we start with MuDetect, which is a state-of-the-art in static API misuse detection at the time. And we find that 28% of its detections are false positives. We arrive through that by detecting misuses in real projects and manually sifting through some of the data, 384 samples. So we look at those samples and we check to see whether we can find some recurring patterns. So we start with our approach, we find some potential misuses, we manually label them. Some of them we're not sure if they're misuses, we're not domain experts, so we set them aside. Some of them we identify as true misuses, so that's good. That's the approach performing adequately. And in 108 cases, we identify them as potentially alternate but correct usages. So these should actually not be misuses. So what we do with them is that we try to actually prevent the misuse detector from detecting them. So we take the original API usage examples that are mined, and we try to figure out whether we can identify transformation patterns on these real API usage examples to prevent these alternative correct usages from being detected. We identified 5 of these transformation patterns. We apply them, we get modify API usage examples, and we apply them to the API misuse detectors to try to improve the performance. So first of all, we want to determine, can we actually improve the misuse detection results? So we start with MuBench and 50 open source projects. We apply our transformation patterns to existing examples. We get our modified API usage examples. We apply them to the approach again, and we manually compare. We find that we can actually reduce falsely detected API misuses by 55 concrete examples. And then we check, are we actually making things worse for the true API misuses? So are we reducing the number of true API misuses that the approach is detecting? So to do that, we use an existing experiment in MuBench, which is the recall upper bound experiment. And we apply our transformation patterns to those API usage examples, and we use them on the exact same experiment, and we manually compare. And what we find is that actually the complementary artificial examples had absolutely no effect on the recall of the API misuse detectors as part of MuBench. So what we've shown is that we can actually use concrete examples, modify them through patterns, and improve the performance of static API misuse without having a negative effect on the recall. If you have any questions, please feel free to ask me. That's all I have for today. Thank you very much.
All right. Thank you, Max. So our next speaker is Diego. Diego, go ahead when you're ready.
Sounds good. I hope my audio is okay. So inside the timer. So thank you very much for joining today. I'm delighted to present our work on the practices of breaking type safety in Go. This work is done in collaboration with Suhaib Mujahid, Rabi Abdelkarim, and Imad Shihab at Concordia University. So this work is about the Go programming language. So this language has been around for 10 years. It has a very clean syntax, modern language features like garbage collector and C-like performance, which really made a go-to language to implement systems like Kubernetes and Docker. And one of the features I'm going to dive in today is the type system of the language. So Go has a very strong and static type system. So if you take a simple function like this and you want to sum an integer with a float, the Go compiler will come and complain saying, well, you're trying to mix different types, right? And you need an explicit conversion. So in Java, this would work. In Go, it does not work, right? So what you have to do, you need to convert your integer to float, and then you're good to go. There's no type violation in this code. So what does that mean is that Go is type safe, which means if your code compiles, you ensure that you have no type violation, no memory, illegal memory accesses, and all sorts of problems that are very costly to fix at runtime, but can be identified at compile time, except if you use the unsafe package. Right, so as with all good things, there's always workarounds, and the unsafe package is basically the feature of the language that allows you to step around the type safety of Go programs. So once you import unsafe, you can do pointer arithmetics. You can essentially manipulate memory addresses. You can, I hear some echo. I hope the audio is okay. You can convert between types, different types, even if those types are actually not compatible, because there is no compiler to check them up for you. And then essentially, the unsafe package is the personification of, with great power comes great responsibility, right? Because you get the power of avoiding pilot checks. You can do. I'm sorry. Okay, I will just continue. So there is memory manipulation. You can do interface with system calls, more flexibility for casting, but you avoid compiler checks. So you're on your own, right? So there's risks of portability, compatibility, and very easy to write bad code. And you don't need to take my word for it. There are plenty of articles on the web showing beware of the unsafe package. You should not use it because performance is never that critical, right? So since we know that this is not, developers are not supposed to use this, we want to investigate, are they actually doing so, right? So are developers using the unsafe package? And if they are using, why? And what are the consequences of it? So we studied 2,500 popular Go software projects, and among them you can see Moby project, Kubernetes, and so on. And we found that a quarter of the projects use unsafe in their code. Yeah, and this goes across domains. This is not only bindings and blockchain, although they occur more frequently there. All domains in our data set has projects that break type safety for some reason. Why do they use unsafe for? So we manually found that they use mostly for system integration, but they also in many cases trade type safety for better performance, right? So essentially trading security or maybe the runtime integrity of a program to achieve better performance in the implementations. So what are the consequences then? We found that the consequences are deployment restriction. That's one of the problems. That means if you use unsafe, you cannot deploy your project in certain cloud environments, such as Google App Engine. You also experience
1 minute warning, Diego.
Okay, thank you. You also experience runtime errors. In one case, we even found that using unsafe led to data corruption in the project. And you also have problems with people using the API wrong because it's very easy to make mistakes. And in one case, we even found a security incident related to misuse of the unsafe package. And the list goes on. There's way more in the paper to discuss. We also received a very nice feedback from the Go team. So we put the paper on archive, and then a member of the Go team reached out to us, and we were able to circulate the paper in the team. And we found that Go team was very surprised that people were using the package as much as they use, and knowing this will help justify spending more time to make the package easier to use. And this has already some positive impact on the language. So patches in Go 1.16 or 1.17, they target some of the shortcomings we report in our study to make the package easier to use for developers. That's it for today. That's basically the summary of my paper. And if you have any questions, please reach out to me, and glad to discuss this at a later time. Thank you.
All right, thank you, Diego. So our next presenter is Aishwarya. And, okay. And Aishwarya, feel free to start when you're ready.
Can you see my screen okay?
Yes.
Thank you, everyone. I'm excited to present our work on mining idioms in the wild. So I'm Aishwarya. I'm a PhD student at UCLA, and this is a joint work with my colleagues at Meta. The main motivation behind our work is that developers often write idiomatic code. For example, to process a data in a vector, common pattern is to write a loop over the elements and compute on it. This is not an isolated example. In fact, we found that such patterns occur all over our code base. And basically, an idiomatic code fragment often has a single semantic purpose, which in principle can be replaced with a functional operator. In this particular case, we can replace all of these using a map API. Now that we have seen some example patterns, an ideal idiom miner would work like this. We have a mining engine that takes in a code corpus and then identifies these idiomatic patterns that recur. And the main observation here is that it can be constructed from a set of nodes that typically occur in a sequence. Before we get into the design of such a miner, why do these imperative code continue to linger? So one of the main reasons that we found was that developers are usually unaware of the API that can replace this imperative code. Or maybe a new API construct is introduced, but then they have not been consistently updated in all locations. Or an API pattern that would simplify this idiomatic pattern is not yet included in the language. Identifying such patterns can help in identifying misrefactoring opportunities, which can help in maintainability and comprehensibility of the code base. Moreover, an approach like this would serve as an educational tool for developers in an IDE or when submitting a pull request. Additionally, the identification of these common idioms can provide data-driven guidance to language developers for new language constructs. So for mining good patterns, we need good representation. On the one end, we have mining idioms from source code that is using the ASTs. While they are easy to compute, they are often very sparse. Additionally, because these are purely syntactic idioms, they are oblivious to semantics, and so they tend to capture shallow idioms. While looking for better tree representation, on the other end of the spectrum, we have program dependence graphs, which are really good at identifying high-level concepts, but then they are computationally expensive and therefore not scalable to a large code base. In fact, Alamanis et al. Proposed semantic idiom loop mining using augmented ASTs, which capture these high-level concepts, but they suffer from several limitations. So the first reason is that since they use an expensive testing procedure in order to identify these data flow patterns, we are unable to use the same thing using the code base that we have at Meta. Second, the lexical ordering of variables lead to different patterns. And finally, different number of read-write statements lead to different patterns. To overcome these issues, we propose J0, an approach that works around the practical complexities of the prior work on idiom mining. We add semantic data flow information as an extension to the AST. And these augmented trees are generated leveraging the cheap syntactic data flow analysis. Our key insight is that semantic patterns can be captured as canonical data flow trees. Finally, we just reuse the Bayesian learning techniques introduced in prior work to mine these idiomatic patterns. This figure provides an overview of our approach. We basically construct data flow augmented trees from a code corpus and use existing unsupervised learning approaches to mine idiomatic tree patterns. Moving to evaluation, in this talk, I will be going over our first experiment where we identify known refactoring opportunities based on our work and also a prior work. So Haggis is a prior work, which is an AST-based idiom mining approach proposed by Alamanis et al. Haggis does not have any data flow augmentation, but is otherwise very identical to J0. We compare precision, recall, and F1 scores. On average, J0's F1 score is 7.1x better than that of Haggis on all the baseline APIs. This shows the effectiveness of the proposed static analysis-based tree representation. APIs also reflect how well the new tree representation can identify diverse patterns. For other experiments, we refer you to the paper. In summary, we have come up with the new data flow substituted AST tree representation that is very effective in capturing semantic idioms. And these idioms mined from these data flow substituted ASTs improve the F1 score by up to 7.1x. Further, we conducted an initial user study with 20 developers who confirmed the usefulness of J0 to suggest potential new refactoring locations. Thanks.
All right, thank you, Ashwarya. So our next speaker is Abbas. Abbas, feel free to start your screen sharing and speak when you're ready.
Hi, everyone. I'm here to present our work on dependency smells in JavaScript projects. My name is Abbas, and in this work, I had the pleasure of working alongside my colleagues Diego Elias Costa, Rabe Abdul Karim, Emad Shahab, and Nicolaus Santales. Our work is focused on dependency management in JavaScript, and a common dilemma in dependency management is the question to update or not to update. On the one hand, we always want to keep our dependencies updated because we want the latest fixes and the latest features, but on the other hand, constantly updating to the newest version might cause stability issues due to backwards incompatible releases. Semantic versioning was proposed to address this dilemma. This standard works by allowing maintainers to communicate whether or not a new release of their package is backwards compatible or not. The way developers would use semantic versioning in managing the dependencies is they would allow automatic updates to new backwards compatible releases. In other words, they would automatically fetch new patch and minor versions, but they would reject the automatic fetching of major versions. The problem, however, is this is not always followed in practice, and developers often opt for alternatives, which could be problematic. So what is a dependency smell? Dependency smells, as we define it, are recurring violations of dependency management guidelines that have negative consequences on the project and/or the ecosystem. We catalog 7 dependency smells in JavaScript. In this presentation, I'm going to focus on the first 4. First, I'm going to show you an example of a dependency smell so you have a better idea of what exactly we're talking about. Here we have a package JSON of a sample JavaScript project. And looking at the dependencies, we can see that the developer has specified jQuery to only use version 3.4.1. In other words, the developer does not want any new updates, any automatic updates to the jQuery package. This, of course, prevents automatic fetching of bug fixes and vulnerability fixes. If we go further down, we see another example of what we call a dependency smell. The MS SQL package circumvents NPM and uses an external link to fetch the package. Obviously, this external link could easily include malicious documents, or it could become inaccessible at any time. But are these dependency smells even harmful? We conducted a survey of 41 practitioners and asked them about the impacts of such approaches. And they gave us a whole set of different disadvantages, ranging from bugs and vulnerabilities to causing dependency breakage and even causing breaking changes. So now that we know dependency smells are harmful, are they even prevalent? Because if they're not prevalent, we shouldn't really be concerned. We conducted an empirical study of more than 1,100 JavaScript projects, and we found that dependency smells do in fact occur in many of these projects, although as you can see here, not all smells occur at the same degree. By looking at the project-wise analysis, we saw that 96% of the projects in our dataset had at least one instance of a dependency smell. We also wanted to see if these smells occurred suddenly or if they were a result of over time accumulation. So we conducted an accumulation analysis, and as you can see, for the majority of the smells in our work, they have been accumulating over time. So now that we know they're harmful and we know they are prevalent in the ecosystem, why do they even occur? Going back to the 1,100 projects, we asked the developers in each of those commits why they opted to introduce dependency smells and received a whole lot of responses. Here we have some examples. So for example, for the panda dependency, a developer mentioned how a new version of a dependency broke their test, so they had to pin to a previous version. For the URL dependency, a developer mentioned how they needed a fix that was available on the GitHub repository but was not yet pushed to the NPM package manager. We categorized these responses, and in general, we can say that dependency smells are a response to dependency misbehavior or shortcomings of the ecosystem. Thank you all for listening. This work has been accepted, and I look forward to hearing your feedback.
All right. Thank you, Abbas. All right. One more presentation, Ying Chen. All right, feel free to share your screen and start when you're ready.
Can you see my screen?
Yes.
Okay. Hello, everyone. I'm Tian Chen, a master student from Beijing Institute of Technology. It's a great honor for me to present our paper, What Makes a Good Commit Message. This joint work with Yuxia Zhang, Clark Stock, Lin Jiang, and Hui Liu. Commit message constitutes an important modality in collaborative software development for sharing knowledge among developers. Each commit should contain both changes to source code and a description message. The quality of commit message is very important. A well-written message explains what changes are made and why those changes are needed. It can help developers understand the code and get involved. Secondly, commit message automatic generation tool may yield an artificial high precision rate when low quality commit messages are used as data size to train their generation model. The left figure shows a well-written message. This state of affairs leaves a number of important open questions. Firstly, there has no definition of what makes a good commit message, and to what extent do poorly composed commit messages exist. Secondly, in terms of semantics, what are required, how these well-written messages are expressed. Finally, feature tools that could help developers in writing good commit messages should be able to recognize whether a written message is good or not. So can commit message of good quality be automatically identified? In the data preparation, we select 5 projects in GitHub and compile the dataset of commits. Before investigating the characteristics, we constructed the standards of well-written messaging. We reviewed relevant studies and visited the related online resources from open source communities and request opinions from experienced developers. Then we summarize that a good commit message should explain the change in the commit, not as what, and describes the reasons for the change, not as why. We manually classified the message based on our definition. We used the semantic analysis to develop a taxonomy that describes how commit message convey what and why information. Finally, we proposed a model to identify this well-written message automatically. After calculating the distribution of these 4 types of commit messages, we found that the quality of messages varies in the 5 projects, with on average about 44% of messages in need of improvement. After manually analyzing the messages that contain neither why nor what, we identified five categories. Each category has its own unique characteristics. By applying semantic analysis, we identified the 5 categories of why expressing way: describe issue, illustrate requirement, and describe objective are directly describe the motivation for the change. The category imply necessity only indirectly explains the need for changes. And the missing why category includes commit messages that don't offer a rationale when it's common sense or easy to infer. We also identified another 4 categories, and the developers have different expressing preference when writing commit messages for different activities. For more details, please read our paper. And then we proposed 3 classification models based on bidirectional long short-term memory to automatically identify whether a commit message is well written and whether a commit message contains why or what. All of them performed well in our dataset and can be reused. Our study has rich implications for developers. Our analysis of how the why and what information is expressed offers developers an understanding of what constitutes a good commit message and prompts them to write better ones. With the help of CY and CWhat, developers can know what is missing in commit message and supplement accordingly. For researchers, our study demonstrates that considerable proportions of commit message are of poor quality, and our classifier CGood can help to construct a large. Thank you.
All right, thank you, Ying Chen. So at this point, let's get ready to discuss the papers with the presenters. Would all presenters please rejoin the room, or the audio video portion of the room? And as that's happening, we already have a bunch of questions from the audience. Thank you to the audience for being so proactive about that. We can start with and forgive me if I'm mispronouncing your name, Matthew Nassif. So this person asks, hi Max, really interesting work. In your longer video, you show an example where a code snippet seems semantically equivalent to a good usage, but just has a different structure. Do you think the clear improvement you show with these additional examples suggests a general shortcoming inherent to current approaches? Or could your transformation rules be integrated with the original approaches at a more fundamental level? Example by defining equivalence classes for ASTs.
Yeah, very, very interesting question. Very good question. So it doesn't, so it's not a general shortcoming inherent to current approaches in the sense that you're right, we could define specific rules to take care of all of these problems by defining equivalent classes for ASTs. And in fact, some of these approaches actually do that for some of the classes that have been thought of already by the makers of these tools. So what we've shown here is that we found 5 patterns that aren't detected by current tools. These could be integrated into current tools. But the approach that we showed to detect these patterns could also be continuously applied to these approaches to keep discovering new patterns that are being missed by these approaches. So the way that we are currently working is by creating these equivalent examples using our transformation patterns, and we can do that offline. So the detection rules for the tools have to be done in real time when the tool actually does the detection, and comparing multiple ASTs can get costly, whereas using the pre-made examples that we can use our patterns that are made using our patterns can be done like ahead of time, and that speeds up the process a little bit. So it's kind of a way to backfill an existing issue. I hope that answers your question.
Yeah, thank you. That's very interesting. Thanks.
Thank you.
Great. So one of the presenters has a question for another presenter. Maybe you can just let Diego ask the question directly.
Yes, thank you. The question is to, I hope you pronounced it correct, Aishwarya. Yeah, sounds good. So I missed this in the presentation. This is all 5 minutes, very short. So wanted to, if you could just talk about what are the applications of mining these code idioms, because I know code recommendation or code completion could be one of them, but are there more applications for this? Thank you.
Yeah, I think so. We started out this whole approach for refactoring purposes. So we wanted to see if we can automatically learn transformation. So that's one of the use cases, and we also did an evaluation study based on that. But apart from that, the other thing was, let's say that a developer is writing some piece of code and they want to submit it before it gets accepted to the code base, they submit it to an IDE, like let's say in like a large company. And so you want to let them know, oh, is it following like the usual code patterns that they are acceptable with, or maybe an API is better to use here instead of this idiomatic code pattern. So that's more like an educational tool, or maybe like just like a hint kind of tool. And then we also thought maybe the third use case could be to help language developers to come up with new API constructs. So let's say that, I mean, we all know that map API exists, but let's say that if it didn't, then you can look at these imperative code patterns and be like, oh, maybe this should be like a map API. So it's more like, again, it's for language developers to identify these new API patterns. But yeah, that's a great question. Thanks.
Fascinating. Thank you.
So the next question is from Matthew again. Matthew, do you want to ask? You joined the room earlier. Do you want to ask your question live again? Yeah. Okay.
It was a clarification for the question. Did you investigate whether the dependency smells the technical lag? And by that I mean the time it takes for a release of a dependency to be included in a distribution.
You kind of cut off at the first part, so I'm guessing you were asking about the relationship between dependency smells and technical lag. Can you be more specific? Sorry, you kind of cut off at the start.
Sorry. Yeah, that's actually exactly what I'm asking. Did you simply see if there's a correlation, maybe packages that add a larger, longer technical lag might lead to more dependency smells.
At the time, we did not specifically try to correlate this with technical lag. We did try to plot this over different packages in terms of age, in terms of size, in terms of their commit activity. But we did not actually look into technical lag at that time, no.
Okay. So, all right. There's another question for Abbas, this time from Jasmine. Jasmine, do you want to ask your question over audio, or I can just read it?
Hi, no, I can ask it. Hi, Abbas, great talk. Yeah, I wanted to know if you've noticed any relationship between the code quality and the presence of dependency smells, and if not, would it be something you would consider in future work or something like that?
Definitely. So we really strictly focus on dependency management, and a big chunk of this kind of boils down to the configuration management of the project, and it is in some sense independent of the code. However, some of our dependency smells, like unused dependency or missing dependencies, these did require us to kind of compare what was declared in the package JSON with what was in the code. And these smells were in fact highly occurring in like more than 70% of the projects we looked at. So I think there is something to be said with code quality when you are but you don't really match what you have in your code with your project's dependencies. But that was pretty much how deep we kind of went into the code. We were mainly focused on dependency management.
Thank you.
All right. So now we have two questions that are from one presenter to another. So one's from Aishwarya to Pick. Aishwarya?
Hey, Vic, thanks for the great presentation. So I maybe I missed this during the talk, but I was wondering how does the variable encoding and decoding works? Because that's mostly like the problem that you mentioned, right? Like you want to know how do you keep your variable, like the context of the variable, but you don't want to keep the name. So I was wondering if it's like a pre-processing step. How does that work?
Questions, yeah. So in the short answer is it's a pre-processing step. So we do the encoding, like if we do the BPE, we feed into the transformer model, and with the pre-process, and it's the same, similar to the prior work, processing for the code abstraction as well. And that's why we see that, if we use the code abstraction, when we do post-processing for the decoding one, then we can't map back to the actual value of the identifiers. But for the BPE, it still keep the values of the identifiers, but instead it's split into the subwords. So then we just simply merge it back when the transformer generates the after version. So then that's why we think that in this way we can reconstruct a new identifier when using BPE. Yeah, thank you.
All right. So and we have two questions from Max next. One from Max to Abbas, and then another from Max to Diego. Max, go ahead.
Yeah. So I'll start with Abbas. So I think you might have read my question, but for the dependency smells, should we start warning users that some packages have dependency smells in them, or should we warn the makers of the packages that they have dependency smells in them so they can fix them, or should we just warn both? Like warn the users, warn the developers? Like, how do you feel?
Well, there's a case to be made for both scenarios. I mean, obviously, first of all, we actually did develop a prototype tool that you can run on your own project, and it will give you a warning like how many dependency smells of each type you have. And that's something that you may want to look at, especially when you want to prioritize dependency management and dependency maintenance. Maybe you want to start off with those types of dependencies. At the same time, the number of dependency smells in a project can be used as sort of a metric to kind of evaluate other packages. So assuming like all other things are equal, you can say, well, this particular package that I'm going to use has a lot of dependency smells. And the thing with these smells is these maintenance issues kind of propagate to your own project. So you may want to be kind of cautious about deciding to depend on a particular project which already has a lot of dependency maintenance problems.
Yeah, that makes sense. Thank you.
All right, and Max, your question
And
for Diego?
Yeah, for Diego. So I mean, like, I really like your talk, and it's really weird to me, right? Like, there's this functionality that's unsafe, and the makers of Go are like, yeah, we want to give this functionality, and apparently people are like, yeah, we want to use this functionality, and so everyone's in agreement that it's good to have this ability to have more control over the language sometimes, and to sacrifice some safety in order to do that. But clearly, like, you found that there are mistakes that are made using this functionality, as you would expect, right? It's unsafe, so mistakes happen. And like, you went and managed to talk with the developers of Go and got them to actually publish some improvements. So that's really wonderful. But do you think we can go further? Like, can we somehow bring some safety to the unsafe package without compromising on the performance benefits that it gives, or the functionality benefits that you found that it gives? Like, do you have some idea of how we can help?
Yes, thanks, Max. We actually, so there, you said it all. So there's something to be said in a package that's called unsafe. And it's actually a quite succinct package. If you look at Java and other languages, they have an unsafe API, which is way more bloated. Go, they're conservative. There's not a lot that in terms of API, but you can do basically everything. Like, you open the door for the internals of the language, right? So there's a couple of things that have been done, which is have better static analyzers that identify some of those mistakes we found. There is now the latest Go 116, not the latest, but Go 116 has already a much more robust check for that. So if you run in a project, you see some of the most common pointer errors you get. And if you do that error, what happens is that the garbage collector can swap the memory while it's processing. So you don't know what's going to happen, right? The best you can hope for is an error. You can have some understanding the deterministic behavior. So there is this, but there's also a more fundamental shortcoming of the language that has been addressed for other reasons, but that could help everyone safe. One of the shortcomings was the lack of generics. So Go didn't have generics until then, and people were using unsafe to generate code and have a more flexible type system. And now the latest version they're proposing, there's a big debate on whether to have generics. I think that could help. We discussed a few other avenues in the paper. So I think there are a few things that can be done, but ultimately it is the flexibility. So if you get the flexibility, a compiler cannot help you, you're going to make mistakes, and developers need to be aware of that.
Yeah.
Thank you.
Thank you.
All right. So the next question is also for Diego, and it's from one of our presenters, Aishwarya.
Yeah. Hey, so I just want to follow up on Maxim's comment and question. So I also thought it was like a really intriguing presentation. Yeah, it's kind of weird that people use unsafe package. So I was wondering if you found like some real security vulnerabilities, because I think you mentioned there were some pointer issues that they did not do correctly. So, I mean, if there was anything interesting that you found and you wanted to share with us.
Yeah, so I do remember we discussed that more at length in the paper. There's two issues that were open that had security repercussions. I wouldn't say that they were vulnerabilities, although one of them, the developers were discussing very explicitly that because they use unsafe, there was some leakage of parameters of the internal API, which could leak some information for the external users that were not supposed to. So this kind of thing could definitely happen. And like I said, you have a garbage collector in the language, so you should not have like C-like pointers, right? So that's how the language result is. You have safe pointers for everything, but if you want to use unsafe pointers, you get what you deserve. So you're kind of saying, oh, well, I want to make memory addresses, but there's a garbage collector just waiting to come and swap the memory out. So we found a couple. They were not the majority of cases, and you can definitely check it out. We pinpoint those because they were very interesting for us. I'm sure there could be more, but we just didn't find too many.
Thank you.
Thank you.
All right. So at this point, I'm not seeing any more messages typed into chat. Does anyone have any questions that they want to ask that have not been typed into chat?
I have one question for Ying Chen, and basically it's a follow up to what you've done in your paper. Do you think we could guide commit messages and how to give good commit messages by having a kind of voting mechanism, right? So developers are told what a good commit message is by having a machine in the background give a good vote, a good score to a comment that agrees with what you found in your research is a good comment structure. So if a developer follows a good comment structure, they get a higher score. If they don't follow a good comment structure, they get a lower score. And then developers they kind of compete to get higher scores on their commit comments. Do you think that could be something that could be automated to kind of give a reputation to developers based on their commit comments?
Hi, Max. Okay, it's a really good question, and to be honest, at present we didn't give a score to any commit messages to developers, but this research topic is very interesting and promising to investigate. It's based on the mechanism and categories we have obtained. What is a good commit message, like it need to include the right information and what have changed. Then we can give a score to developers. At present, we can tell commit message whether it has the right information or what information. These suggestions can guide developers to improve the commit message.
Okay. Thank you.
Thank you.
All right. So we still have 8 more minutes. Any other questions at this time?
I have a quick question to Max. So may I just go ahead and ask? So Max, so if I understood correctly, so you went through the patterns, first qualitative, so semi-manually, and then you find those patterns that can use to generate those examples. In your experience, how well this can be generalized to, because like each API is kind of a different universe somehow, right? So are these things that you can generalize for the language, so other APIs in the same language, or the things that can even go beyond that, or there are some limitations on this? Mm-hmm.
So the patterns that we identified technically work across Java.
Mm-hmm.
So like certain API. So one of the patterns, I'll just give you a quick example, is the pipeline pattern. So certain APIs can be pipelined and some can't. And then the problem is that when you can pipeline, you can do it in one long string, or you can keep calling the object and call the different stages of the pipeline on the original object. So there's 2 ways, and you can do that in however many steps you want, right? Like you can do 1 long pipeline, 2 short pipelines, 3 like shorter pipelines, depending on how many steps you have. And the problem that we found is that depending on which one is most frequent, that will be seen as the correct pattern. And then everything else will be judged as potentially wrong. And so what we do is that we inject all the possibilities of the pipeline. So we either take it apart or we put it back together, and then we inject all the stages so that all the stages become equally frequent and are all acceptable for the pattern detection algorithm. So that technically would work for any API that is pipelinable across Java. Of course, that also technically would exist in other languages, so we could apply it for, let's say, C# also has this concept. But yeah, I think there are definitely patterns that are more generalizable than others, and there are definitely some that are more applicable than others. And in the paper, we go into details on like which patterns were most frequent, and we didn't specifically look at any one API. So we looked across like any API that appeared in our data set, and we randomly chose the projects that we used. And so, yeah, technically they're generalizable across Java. Across other languages, a bit trickier, but maybe. And then, yeah.
And do I need to apply those patterns and generate more examples? Do I need to already, based on the patterns you just told me, there are some that works for certain APIs that don't. So for me to apply this, do I need to have the domain knowledge of the API, or there's a sort of a semi-automated approach that can extract those?
As part of the paper, as part of the replication pattern, we have an automated tool that will go through your examples for you and identify the ones where the patterns can be applied and apply them, or at least safely applied. There may be cases where we could apply the pattern unsafely. We don't do those. But
okay.
Yeah.
Awesome. Thank you.
You're welcome.
Okay. So 5 more minutes. Does anyone else have any other questions? So in that case, I have a question for Pick about auto transform. So based on your presentation and looking at the paper, I'm not so sure how I guess time efficient or expensive your technique might be, because I think NMT, neural machine translation, can be pretty expensive. I don't know how expensive byte pair encoding can be, and I guess maybe the kinds of transformations you're applying are pretty small, but I wonder if you could speak more towards the efficiency of the transformations you're doing.
Yeah, so we actually have a discussions about the efficiency, the computation time. But to be honest, I don't remember exact number, but basically the RNN architecture is lower than transformer architecture because the RNN architecture is compute in a sequential way, but for the transformer since it compute in a more parallel, so it's faster even though it's do lots of computations. And so I think that our approach, which use transformer architecture, is generally faster than the RNN architecture. But in terms of the practicality, like in terms of the applying to the practice, I still think that it still needs some effort to build, and then even if we want to apply on the larger set, yes, it might take more time to compute and more resource. Yeah.
Okay, thank you.
Thank you.
So we have 3 minutes, so I think that gives us time for maybe one more question if anyone has any. Okay, in that case, so how about this? This is kind of a question maybe for maybe for Ying Cheng in particular, or the people working on that paper. So in terms of good commit messages and code review, how do you think someone could use the results of your work to help improve the code review process? Can you elaborate on that some more? Because I know you built a taxonomy and so forth, and then you did like this empirical study. But I mean, what are the most concrete recommendations you think you can make for let's say like practicing software developers?
Okay. Hello, Joshua. Okay. Thank you for your question. And this is really a good question. To be honest, at present, given the results we have obtained, we can offer developers several guidelines towards how to write the reasons about the code change and what they have made changes in commit. But to be honest, I don't think our results can offer any help to the code review activity